we want to look at now, we're looking at section 4.3, and we're doing properties of logarithms. And there's basically 4 major properties we're going to look at. And I'm going to go through them, prove them. I just want to mention a helpful source for this was a website. I'll send the full link out with the exact location. But chilimath.com. And I'll send out the full link to the page that talks about these proofs. So the thing I want to look at is the properties. And the first property has to do with relationship between products and sums. And it's this one. The logarithm of m times n is equal to the logarithm base b of m plus the logarithm base b of n. So the way we can do this, let's see here. All right. So what we can do is this. Let y be log base b of m. And let's let x be log base b of m. So what this implies, b to the y is equal to m. B to the x is equal to n. And just to be consistent with how we did this before, let me rewrite these, because we have this counterclockwise way of doing it. So the log base b of m equals y, so b to the y equals m. And log base b of n equals x, so b to the x is equal to n. And there we go. That's a little more familiar. All right. So what we're going to do is this. Let's multiply b to the y times b to the x. And so when we do this, we get m times n. Now, if we multiply these together, we'll get b to the y plus x. And I mean, this stays the same. This is just simplifying. Now take log base b of both sides. So the log base b of b to the x, I'm sorry, y plus x, well, that's log base b of m times n. And again, with the log base b, exponential base b, those cancel. And so what we get, y plus x equals log base b to the m times n. Again, this inverse property makes those go away. But remember what we called y. Y was log base b of m, and x was log base b of n. So we get this. All right. And so this is going to be the result. And again, check out chilimath.com. I studied that page a little bit to get started on these. They were helpful. So that's how we can prove that property. Now, how does it work in practice? Well, let's take a look. So what it says is this. Let's say we have log base 5 of 7 times 3. Well, we could rewrite this as log base 5 for 7 plus log base 5 for 3. It lets us break things up. So let's see here, find a good example of that. So if you have, say, log base 2 of x, y, and z, well, you could actually break this into a sum of 3 things. Log base 2 of x plus log base 2 of y plus log base 2 of z. So it goes the opposite direction. We can take the log of a product and turn it into a sum. All right. So let's take a look at another property. And it's the log base b of m over n is log base b of m minus log base b of n. So this says when you take the logarithm of a ratio, you're going to get subtraction. So the logarithm of a product gives you addition of logs. Logarithm of a division is going to give you a difference of logs. So let's prove this one. And again, we're going to approach it sort of the same way. Log base b of m, let this be y, log base b of n, let this be x. So this means b to the y equals m, b to the x equals n. So what we're going to do now is look at the ratio of these. Well, this would be equal to m over n. And then we simplify this side. We get b to the y minus x equals m over n. Now we take the logarithm of both sides. So log base b, and we choose log base b because we want to make this base for the exponent cancel with the log. And sure enough, that's what's going to happen. Remember what x and y were, for y and x, it was log base b of m minus log base b of n. Well, this is log base b of m over n. And now we've proved our property. So for example, if we have something like this, say natural log of 7/2. Now remember, this is log base e. We can rewrite this as natural log of 7 minus the natural log of 2. Now we try something a little more complicated. Let's go backwards. Let's say we have the natural log of x squared minus 1 minus the natural log of yz. Now what this means is we're going to take the ratio of this over that. This is like m, and this is sort of like n. So we get the natural log x squared minus 1 over yz. And that's going to be it. Now let's take a look at another property. And it goes like this. The natural log of b, and there's some m, and here's a p here. We've got, now these are not the same. I mean, they could be, but be all right. This is equal to p times the log base b of m. And it doesn't matter, these aren't the same. It's when these are the same, the two bases, are when things cancel. But when the exponent itself and the base, that doesn't matter. It's only when the two bases are the same is when things cancel. But the point here is this. The exponent will hop down from whatever this is and go in front of your logarithm. So how does this work? Well, let's take a look at y. Well, log base b of m to the p. Remember, this is repeated multiplication. So log base b of m times itself p times. And so what we can do is we can use our addition rule. Say this is log base b of m plus log base b of m p times. And then when you add something up, p times, that's the same as p times log base b of m. And so that's going to give us our property. So we start out with this, and we're ending with that. So how does this work? Well, let's say we have this. Well, let's rewrite this as x with an exponent. So this would be the natural log of x to the 1/7. And according to this property, this will hop on down in front of our natural logarithm. And so we get 1/7 natural log of x. And there we go. Now we could also go in the opposite direction. We could say this. Two x log base 5 of y. We can take this entire thing, take these, remove these for now, 2x log base 5 of y, and we'll move this as an exponent of y. And there we go. So there's one more property to look at. And this is a really powerful one. The reason being, you see me up here talking about log base half, log base 3, log base 2, but we only have log base 10 and log base e on our calculator. So what do? How do we do log base 3? Well, there is a way you can do it. It works like this. Log base b of a, you can write as log a. Let's give it a, say log base n of a over log base n of b. So basically what this says is this. If we have log base 3 of 7, we could rewrite this as log 7 over log 3. We can choose this n to be anything we want. So we could do log base 10 of 7 over log base 10 of 3. That'll give us log base 3 of 7. Or we could have just as equally used natural log 7 over natural log of 3. That would have done the same thing. So this means if we have a logarithm of a base that's not on our calculator, we can rewrite it in terms of log base 10 or log base e. We'll get the same answer. So let's take a look at this. Why is this true? Well, let's start out. Say this is equal to y. So this means that b to the y is equal to a. So starting with this, b to the y equals a, let's just take log base n of b to the y equals log base n of a. We take log base n of both sides. Now, using our power rule that we just learned about, that means y log base n of b equals log base n of a. And so now we divide, we solve for y, and so we get y is log base n of a over log base n of b. Now remember, this is what y was also equal to. So what this says is that log base b of a, which is y, well, here's y, that's going to be log base n of a over log base n of b. And there we go. So again, this lets us come up with logarithms that are not on our calculator. So for example, let's go back to log base 3 of 7. Well, according to our rule, we can write this as log base 10 of 7 over log base 10 of 3. And if we put that in the calculator, we get 1.771243749 approximately. It goes farther and farther. And what if we use natural log though? Well, according to our rule, it doesn't matter what base we use. So we could say natural log of 7 over natural log of 3, and we put that in. Sure enough, we get the same thing. So it doesn't matter what log base we use, we're going to be all right. We'll get the same result. All right, so let's play around with these. We're going to bring all these properties together, and we're going to build things, compress them, and then we're going to actually pull them apart. So let's say we have something like this. Well, the logarithm of a division is the difference of logarithms. So this is log base 4 of 64 minus log base 4 of y. Now, does this have an evaluation? Because remember what a log is asking for. It's asking the base to some exponent gives you this result. So the logarithm always kicks out the exponent. What is the exponent? That's the output. So this to some output exponent gives you this. Well, do we know this? So log base 4 of 64 equals n, or 4 to the n is 64. And do we know this? When we actually do, well, you might be able to figure it out. n equals 3. Now, of course, you could figure this out on a calculator. We could just take log base 10 of 64 divided by log base 10 of 4, and you're going to get 3. Or you could have done natural log of 64 over natural log of 4. This is totally cool. This is great. Still going to get 3. So what we end up getting at the very end is 3 minus log base 4 of y. And that's it. Now, typically, we don't always get a logarithm that's going to give us a non-irrational number. This comes up with square roots, like square root 3, square root 2, square root 5. And when we get square roots that are going to give us an irrational number, we don't try to write out square root 3 as a rounded off decimal number. We just leave it as square root 3. Same thing with logarithms. If you get logarithms and you say you did log 64 divided by log 4, you got this irrational number, just leave it as log base 4, 64. But this one, we tried it out and it comes out to a whole number 3, or a rational number, which is nice. So there we go. All right, let's keep going. Let's see what else is here. Let's say we have this. So initially what we have is a logarithm of division. So that means we're going to subtract. So log base b of x squared y minus log base b of z. Logarithm of the numerator minus logarithm of the denominator. But this is a product. So this will break down to log base b of x squared plus log base b of y, and then we still have this over here. And there we go. And this has an exponent, and we have a property that says the exponent hops down in front of the log. So we have 2 log base b of x, and we still have the rest of it, minus log base b of z. And there we go. So there's one we can look at. Now let's try another one. Let's say we have something, ooh, how about this? Log base 2 of the 5th root let's see, 5th root x y to the 4th over 16. Wow. First thing we're going to want to do, though, let's make this into a power, an exponent. So this is log base 2, and really what this is all of that to the 1/5. Remember, roots are just exponents that are fractions, 1/5. So that's going to be very helpful here. Now that we've done that, we see we could use our exponent rule for logarithms. This will hop down in front of a logarithm. This is 1/5 log base 2 xy to the 4th over 16. I want to be careful here. I'm going to recommend putting this in parentheses. And the reason is this whole logarithm is going to break up, and this 1/5, it's multiplied to this entire thing. So when this breaks up, it's going to be multiplied to whatever the pieces are floating around in here. So we've got a division. So this will be log base 2 xy to the 4th minus log base 2 of 16. And we could try to figure out what this is. Let's see if it comes out to something that, well, it's like some kind of rational number, some fraction or whole number. So let's go with natural log. Let's try that. Natural log 16, natural log 2. And if you do that, you're going to get 4. Comes out to 4. Well, that's awfully nice. So 1/5 log base 2 xy to the 4th minus 4. And now what we can do, we can break this up. This is a product of x and y to the 4th. Log x base 2 plus log base 2 y to the 4th minus 4. And then this one has an exponent, it can hop on down. And there we go. Well, let me double check something with that one. Just curious if they want you to distribute the 1/5 or not. Let's see if they want you to do that. They do want you to distribute the 1/5. So you're going to have 1/5 log base 2 of x plus 4/5 log base 2 of y minus 4/5. So they do want you to distribute this 1/5 at the end. All right, let's see here. What else do we have? And then sometimes they might, let's see. Here's an interesting one. You might get this. Natural log x cubed square root x squared plus 1. X plus 1 to the 4th. So again, let's deal with this division. We have a division here. It means we're going to be subtracting natural log x cubed square root x squared plus 1 minus natural log x plus 1 to the 4th. And in this one, we can use that exponent rule. That's the best we can do for that. Now this is a product of x cubed and square root x squared plus 1. So this will become natural log of x cubed plus natural log square root of x squared plus 1 minus 4 natural log x plus 1. And this we can treat as being a power of a half. So this half will hop down in front of the ln, and so this 3, it'll hop down in front of the ln. So we get 3 ln x plus 1/2 ln x squared plus 1 minus 4 ln x plus 1. And this is as far as we can go. We don't have rules for the natural log of a sum, so we just have to leave that. We do have the rule that the natural log of a product is the sum of natural logs, but the actual logarithm of a sum We don't have anything for that. So we're just going to leave it. Since this x squared is part of this sum, we can't actually get to that exponent. This is the logarithm of an object that has an exponent, so we can have that exponent hop down. But this is buried inside the sum, and we can't get to it. So we got to leave that one. But this will be our answer. So it brings up some issues, and something to point out. The author mentions this too. There's some incorrect uses of the properties that are very easy to make. So things that are not true. And that would be the log base b of a sum. This is not. And this is the not true. It's not true that this is the case. This isn't true. If it's a product, it's true. This is correct. This is good. But it's not true if you have this. We don't have a log property for a sum, just a product. Same thing with the difference. Log b m minus n. We don't want to say this. This is not true. Now, if we had this, a division, then this would be fine. But since we have a subtraction, it's part of the not true group. We don't have a rule for the logarithm of a division of a difference. So you want to be careful of those things. And then when you have embedded exponents, like we have natural log of x squared plus 1, this is not equal to natural log x plus 1. That is not true. What we can do, if we had natural log of just x squared by itself, this entire object for taking the natural log of, that would be natural log of x. That's true, 2 natural log x. But this is the object we're taking the natural log of, and so this is the place where we would look for an exponent, not inside that object. We look for an exponent out here that could hop down. Exponents inside won't hop down. All right. Let's see some other ones the author mentions. So internal exponents don't hop down. Some other ones the author mentions. Log base b of m over n. This isn't true either. Log base b of m over log base b of n. This is not true. Remember, when you have the log of a division, it's the difference of logs, not the division of logs. You'd have log base bm minus log base bn. And same with multiplication. Again, this is not true. It would be true if we wrote this. Remember, the log of a product is the sum of the logs, but it's not true that the log of a product is the product of the logs. So just some things to point out. So let's do something else. All right. Let's say we have this. If we can pull things apart, we can also bring them together. So let's say we have log x plus 3 log y. Well, in this case, what you could do is we have a sum of logs, and they have the same base. So another thing I need to mention with these properties, they must have the same base to work. If you have different bases, they're not going to work. So these are both base 10. So that means we can pull them together. But before we do that, we've got something in front of log y. So we can rewrite this as log y cubed. And because these logs have the same base, we can glue them together. Log xy cubed. And we're good. Now, if these had different bases, we couldn't do this. It wouldn't work. So let's say we have something like this. All right. Well, first thing we can do is deal with what will become exponents. This will be ln x plus 6 to the fourth minus ln x cubed. And since this is a difference of logs of the same base, in this case base e, that's going to be a division or ratio of those logs. Or not the logs, but what's inside the logs. I'm sorry, not a ratio of the logs. That's one of the things we're not supposed to do. But there we go. That's what we're going to get, a logarithm of the ratio. All right. So let's say we have something like this. Let's say we have 1/2 log base 5 of x plus log base 5 of y minus 2 log base 5 x plus 1. Now, first thing we're going to want to do is, and there's ways we could look at this, but probably the best thing to do is to distribute the 1/2. So we're going to get 1/2 log base 5 of x, 1/2 log base 5 of y, minus 2 log base 5 of x plus 1. And then now let's deal with these numbers in front of the logs. They're going to become exponents, and let's leave the sign here. I'll leave that sign. So we get log base 5 x to the 1/2 plus log base 5 y to the 1/2 minus log base 5 x plus 1 squared. Well, let's take care of this sum. With this sum, that means multiplication. So the log base 5 will now contain x to the 1/2, y to the 1/2, minus log base 5, that's a 5 there, x plus 1 squared. And now finally we combine these into a single log using the fact that the difference of logs of the same base will give you a log of a ratio. So this will become log base 5 of x to the 1/2, y to the 1/2, and then x plus 1 squared. And then we can do some simplification. this would be x times y to the 1/2 over x plus 1 squared. And this is just a square root. So log base 5 square root of xy over x plus 1 squared. And that's going to be your answer. So that's it for the properties of logarithms. If you have any questions, let me know.